we discuss a notion of quantum phase, and which is the equivalent class of a sequence of Hamiltonian as the size of system go to infinity. And so one of equivalent class is contain the product states, which correspond to trivial phase. Okay. Then the other Hamiltonian in this equivalent class may have ground states, which we call short-range entangled. They are related to the product state by the so-called local unitary transformation. And this equivalent class defined by this local unitary transformation really correspond to a quantum phase. If Hamiltonian have a symmetry, then the corresponding equivalent class may have a symmetry breaking phase. So now we consider the case where Hamiltonian have a no symmetry. And then the question is that, do we have other equivalent class? Certainly one of the equivalent class is a short-range entangled class, which is called a trivial phase. But there should be, we believe there should be some other more complicated wave function on the Hamiltonian, which is not connected to the product state by this local unitary transformation. And that kind of a new equivalent class correspond to so-called topological order, new kind of a quantum phase beyond the symmetry breaking. So this is also called a long-range entangled. So therefore, the topological order we mentioned the last lecture is really a pattern of a long-range entanglement. All these equivalent class and the local unitaries, but they are not connected to the product state. And also, there are different patterns of long-range entanglement. They are not connected to each other by these local unitaries. So this is really a point of view of a topological order from an entanglement angle. Okay. So so how to have some intuition about these long-range entangled states? And here we want to give some examples. First, the short-range entangled states is just a product states of some local deformation of these product states. And to have a long-range entanglement, we need to sum over many different product states. Like we sum over all pattern of a spin, like up and down, sum over all spin patterns. But if you do that, that's too much, because when you do that, this kind of summation for all possible spin pattern, a superposition of vectors, correspond to the product states where on each vertex, on each side, we have up plus down. Then tensor product on all sides. So actually, if you do too much, we end up with nothing. And this is still product state. So, so there are two ideas to get something which is very different from product states, which is hopefully is long-range entangled. One idea is to modify the coefficient. Here, when I make a superposition, the coefficient all the same. They are all equal to 1. And we can make a superposition with some kind of a different coefficient here, where this zi is a position of i's upspin. A downspin is a background. For the upspin, they have a position that's in 2 dimensions, using the complex number to label their position. And then we can have this kind of a wave function. Actually, this wave function corresponds to so-called chiral spin states or fresh quantum Hall states. They have this type of wave function. And that's actually is a long-range entangled. And there's another approach, which is we do not sum over all configuration. We sum over a subset of configuration. So in this lecture, we will mainly discuss the second approach. So how to pick up the subset of spin configuration? Well, we view the upspin as a background, okay? Then the downspin may form strings, okay? So this is a special kind of a spin configuration. And then we sum over this kind of a configuration where the string can have different shape and different size and position. So we sum over all possible loops. So this string is a closed string. So we sum over all possible loops of down spins. And this is a partial summation. And that's end up with a highly entangled states. And we can also modify the coefficient. For example, we can put the plus minus 1 sign here, depending on number of loops is even or odd. And then that's another wave function and maybe another entanglement. So this is give you some kind of example how to construct long-range entangled states. But however, when you write down the wave function arbitrarily like this, there's a concern that maybe this wave function is kind of illegal in a sense it can never be a ground state of a local Hamiltonian. Remember, Hamiltonian only have a local interactions. And local interaction can only do certain things. It may not be able to pick this wave function as a ground state. In particular, second one is of a concern because to determine number of loops is not the local property. We cannot examine this local part of this system and to see how many loops are there. So looks like the second wave function may be illegal because the number of loops is a global property. Okay. So to see whether wave function is legal or not, there's one important thing this using this local dancing rule. You know, those spin have a superposition. We can think about dancing pattern, and each spin follow a dancing rule. They organize into a global dance. Okay. And so what is the local dancing rule to have a string liquid? And we can have a first rule is that all the down spin hold the hand. So the string do not have end. Okay, the string are always closed. That's first rule. The second rule is that otherwise the string can deform freely. The string can change its shape, you know, can move around. Or the string can reconnect like that. The first they have this we call this IH move. They can reconnect. They can break. Yeah, this is a special class of correlated states. And then, these two rules are local because by examining the system locally, we can see whether the string is connected or not. Is string have end or don't have end. And these two moves are local moves. So the wave function, these two wave functions have the same amplitude, and these two wave functions have amplitude, same amplitude if the string configuration only changes locally. So this local dancing rule can be imposed by the local Hamiltonian. Actually, this local Hamiltonian is a well-known Torah code model. Okay, and actually, this local rule also kind of sufficient because by applying this local rule, we can determine the global wave function completely. Because every string, closed string configuration are connected by these local rules. So all the wave function amplitude is the same. We can choose that to be 1. So therefore, this equal weight superposition, this first wave function equal weight superposition indeed can be imposed by local rules and can be realized by local Hamiltonians. And there's then let's consider another rule. Another rule seems trickier because when a string reconnect, there's a sign change. Okay, we allow this sign change. So this actually also local rule because in 2 dimensions, like this example, you can see that if you make a reconnection from here to here, we get actual loop here. So you can convince yourself that every time you make a reconnection, the number of loops changes by 1, either increase by 1 or decrease by 1. So therefore, this local rule change the even oddness of loops. So from here, you can see that if we modify this second local rule, we get the global wave function, which is whose amplitude is a minus raised to power of number of loops. Even loop is a positive, odd number loop have negative amplitude. That's kind of superposition. Okay. And we also see that Actually, this only works in 2-dimension, because in 3-dimension, you can see that we allow this over-under crossing. And this kind of a local reconnection do not change the number of loops. So therefore, this wave function is okay, it's a legal wave function for 2-dimensional system, but illegal for 3-dimension. It's kind of inconsistent wave function. Okay. So so therefore, in 2-dimension, both wave function is okay. In 3-dimension, and the second is not okay, but the first one is also okay in 3-dimension. So equal superposition can also be realized as a 3-dimensional liquid phase. Okay. And I mentioned that the topological order are probed by this ground state degeneracy. So now we have a two-wave function, which is a superposition of the wave all the different loops. And there's a question: are they have a non-trivial topological order or not? And so basically, we ask whether they have a ground state degeneracy on the torus. We try to put these two-wave function on the torus to see do they have a non-trivial ground state degeneracy. And the answer is yes. Actually, the both wave function have a 4-4 degeneration on torus because they have 4 sectors. And to see the 4 sector, we can draw a line, and we ask how many string crossing this line. Here, they're even for the horizontal line, and also even for the vertical line. So that's even sector. And this one is an odd even sector. So for horizontal line, there's odd crossing, and etc. So we have 4 sectors. Okay. The important thing is that these 4 sectors are locally indistinguishable. So this is the key feature. And this feature is related to quantum entanglement. The quantum entanglement have a special property where if you know the every part, you may still not know the whole. You know every part means you know locally, if you examine part of system, and you can examine every part of system, you know every part of them. And from this information, can you reconstruct global wave function? The answer is no. If a wave function, global wave function have entanglement, and knowing local part may not have enough information to know the global wave function. Another way to say that these 4 sectors really representing 4 different global wave function. And these different global wave function actually have identical local parts. They locally look the same. Because when you locally look at this string liquid, you don't know whether this string is a wrap around the system or not wrap around the system. They just locally fluctuate randomly, and it's the same. So certainly there's a more rigorous way to express this idea. And here I just use some cartoon picture to say that. And this actually is a origin or mechanism for ground state degeneracy. Remember, the topological degeneracy is one of a defining property of a topological order, this concept. So therefore, we see that the mechanism for topological order is a long-range entanglement, because the long-range entanglement allows us to have a situation where we have different global wave function with identical local parts. And the identical local parts imply any local perturbation cannot distinguish them, cannot lift degeneracy, and that's how we get the topological degeneracy. So therefore, this kind of enforce our idea that the topological order is really a pattern of long-range entanglement. And so really a study of topological order is really a study of a quantum entanglement. It's just that in 1989, when we studied topological order, at that time, the quantum computation is not fashionable at that time. So the notion of quantum entanglement is not very popular. Now, because of quantum computation, the quantum entanglement is a very, very well-known, very popular idea. So I mentioned that now, but we have 2 wave function, one with a sign change, one don't have a sign change. It turns out that both wave functions have the same ground state degeneracy, and the torus is a 4. And the genus 2 Riemann surface is a 4 to the second power. So actually, in general, it's a 4 to the g's power. G is the genus of Riemann surface. So actually, these two wave functions have identical ground state degeneracy. So there's a concern that maybe these two wave functions belong to same phase. They belong to same equivalent class, and they have same topological order. Although the wave functions are different, they are similar. So to really study whether they are similar or not similar, we want to study something more than ground state degeneracy. And we have mentioned that to go beyond the ground state degeneracy, we can using so-called this vector bundle in the moduli space to get more information. But here we'll go to another route. We'll study excitations. So if a string are all closed loops, and then that means the ground states. So the fluctuation of loop is the ground state. So what is the excitation? Excitation are open strings. When you have open strings, this open end represents the defect at the cost energies. But however, the middle part of open string is merged with the background closed string. It's not observable and don't cost energy. So only when you have open string, it do not represent a single extended excitation. Actually, an open string here representing 2 point-like excitation. Only the end point can be distinguished from the background closed strings. Okay. So therefore, this end of string representing the excitation. Okay. And from here, we can see that this end of string have a special property. They are topological in the sense that they cannot be created alone. Because when you add a single string, we always add 2 end. There's no way to add a single end, so that's one sign. This point excitation is topological, cannot be created by any local operator. Okay. And so now next question we ask, what is the property of those excitations? And you may say, oh, whether it's a boson or fermion, what is spin? But here we ask a more fundamental question. What is the internal degree freedom? Like a spin half electron have spin up, spin down, have a 2 degree freedom internally. But whether this end of string carry any internal freedom? And to answer this question, we consider a sphere, a space sphere. We put 4 end of string on the sphere, like this. That's 4 end of string. But here we can see that there are two sectors. Either this 4 end of string can be connected this way or connect that way. So it looks like there's a 2 sector. There are 2 degenerate ground states. But actually, it's not right because we allow this kind of fluctuation, this string reconnection fluctuation. So actually, this sector and that sector are connected by this kind of string reconnection fluctuation. So they belong to the same sector. So in fact, when you have a 4 end string on the sphere, there's only 1 sector, only 1 ground state. More generally, we can see that when you have a 2 end of string on the sphere, they're only unique ground states. And that means once you fix their position, there's no degree freedom. You have unique ground states. So therefore, there's no internal degree freedom. So this end of a string is like a scalar. There's no internal degree freedom. Okay, that is an important thing. And here I want to mention that in addition to end of string, there's another type of a topological excitation, which is a little more subtle. And remember, whenever you have an excitation, you just modify the wave function. And here I want to say how I modify the wave function. The ground state is equal to superposition of all possible loops. Okay. And here we modify the wave function by adding a plus minus sign. The plus minus sign is that how to give this plus minus sign. We have following rule. We first pick up a location. It's called X. We pick up a spatial location. Then we count number of string loops wrap around this location. If a number is even, the sign is plus. If a number is odd, the sign is minus. So basically, this cross is like an insertion of pi flux. And the string is like a borderline particle, which is C, the pi flux. So we call this M excitation. It's also point-like excitation. And this point have an actual energy, but other part have no energy density, and this one have an energy density. So this is another type of excitation. Okay, and so now let's ask a question: whether this under string is a boson or fermion. And but before I do that, let's ask whether this under string carry spin or not, carry orbital angular momentum or not. To do that, we just do rotation. So let's do some trivial rotation. We do the 360 rotation. Okay. So you can see we have under string, which is string going downwards. When you do this 360 rotation, we go from the straight string, we go from the straight end to hooked end. Okay. And but then this hooked end maybe connect to the straight end by fluctuation, but not actually. If you do the string reconnection fluctuation at this neck here, we go from right hook to left hook, but we never go back to straight. Okay, so that means the string end have two sectors, straight and hooked. But if you do rotation, if you do two 720-degree rotation, then this double hooked is connected to straight. So therefore, this 360 rotation is non-trivial. It's a exchange straight sector to hooked sector. So it has this 2x2 matrix. And this 2x2 matrix have two eigenvalues, +1 and -1. The +1 eigenvalue means under 360 rotation, there's no phase change. So that's spin 0, integer spin. But the -1 means that a fractional spin, because under 360 rotation, we have a -1 phase change. So that means the spin is a fractional. So this is an example that this Lagrange entanglement of topological order can give rise to this fractionalization. Here we have a fractionalization for angular momentum, a fractional spin. And this is also called a topological spin of excitation. This one have a topological spin 0, and this one have a topological spin 1/2. And we know that there is a spin statistical theorem that spin 1/2 should be fermion. So indeed, this spin 1/2, we can use a cartoon picture to see the spin, to show spin 1/2 is a fermion. Because when we have an exchange of a two string end like this, from here to here is an exchange, then we can make this two reconnection move and to go to here. So if we find that exchange is like a 360 rotation of one string end. Okay, and so that means if a 360 rotation gave us a -1, that means exchange also gave us a -1. So that is spin statistical theorem. And so this spin 1/2 is a fermion, spin 0 is a boson. Okay. So in general, we have a more excitation. So here we already have two excitation. This spin 0 string end we call the E. This fermion we call the F. That's a fermion. Remember, we have another excitation M, which is a even string have plus sign. The odd string wrapped around it have a minus sign. So here is just a even and odd with a minus sign. So that's M. And we notice that from this picture, we see that the difference between E and F is actually M, because you can see the straight one and the hooked one differ by a string wrapped around this point. And the wrap around this point with a sign change or without sign change is a difference of M. So actually, we can view this F as a fusion between E and M. This fusion with M changes the sign of the hooked one. So we'll get this fusion rule. So therefore, this F can be viewed as a bound state of E and M. And certainly, we can also view M as a bound state of F and E. So in general, we have this general fusion rule. And the one here represents a trivial excitation, which can be viewed as this way. It's a trivial excitation which can be created by local operators. So therefore, for this string liquid, we have four kind of extension. This 1EFM, and they have this kind of fusion rule. So that's kind of describing the topological extension in this kind of string liquid. So actually, this kind of top excitation is familiar. Actually, it's correspond to this two-dimensional Z2 gate theory. In the Z2 gate theory, we have Z2 charge, which corresponds to E. We have a Z2 vortex, which corresponds to F, M. And the bound state E and M give us fermion, which is F. And certainly we have trivial excitation, which is a 1. So it turns out that the property, the physical property of our string liquid is identical to the property of Z2 gate theory, which is the simplest so-called topological quantum field theory. So therefore, we can say that the string liquid we just described have a low energy effective quantum field theory, which is topological quantum field theory. So there's a connect to a condensed matter Hamiltonian system to the topological quantum field theory. So that's a topological order also described by the topological quantum field theory. So that's the connection here. And then for the other string liquid where reconnection have a sign change, then we find that the end string have different statistics. It's really because when you do this 360 rotation, we get a right hook. But to go from right hook to left hook, we need this reconnection move. So that's with actual sign move, actual sign. Then we do another 360 rotation. This left hook became straight again. So therefore, for this kind of, for the second string liquid, the 360 rotation is this 2x2 matrix with its actual minus sign because this reconnection move has have actual minus sign. And then their eigenvalue will be I and minus I. So that means the spin a quarter or minus a quarter. And then actually they have a sammian because quarter spin corresponds to sammian, a statistics between both and the sammian. And so therefore the second string liquid is called a double sammian topological order because I have two kinds of sammian. S plus have a spin minus quarter, S plus have a spin plus quarter, and etc. And this double sammian topological also have a topological quantum field theory to describe it as effective theory. And this topological quantum field theory have two U1 transaminant term, A and A tilde. And so in general, from here we can see that these two string liquid although have same ground state degeneracy, but they are really have different topological order because their excitation have a different statistics. And this Z2 topological order is for this Torah code model, and we have a double sammian topological order and for the second string liquid. Okay, so that is just two very simple example of topological order. Okay. So I think audience will come to raise any question any times. Okay. So so in addition to this loop liquid, actually there's something more complicated, more general. Is that we can allow string to branch like this. The three string can reconnect. Before we say the string cannot end, cannot branch. But here we say string cannot end, but they can branch. The different rule, different dancing rule. So here we get so-called a string net because the string form a network. And the dancing rule is more complicated. One is that the wave function with different, if you deform the string, the wave function is not changed. But however, if you reconnect the string, the wave function have a more non-trivial change. Like a wave function of this kind of string configuration, the superposition of the other two string configuration. Before, if you don't have second term, we don't have from here to here, that's a reconnection move. But here the reconnection is more complicated because we allow a third string to be added here. And the consistent condition also became non-trivial. So there's a coefficient here happen to be given by this gamma. And if you're given by gamma, this we got a consistent dancing rule. So what is a topological extension? Again, we can consider end of string as a topological extension. And we can put the full end of string on the sphere and to see how many locally indistinguishable states are there. How many ground state degenerate ground states. And maybe there's 4 states because we have different sectors. We have maybe 4 sectors. But we know that this thinking is too simplified. It's because they can reconnect. Maybe those 4 sectors are connected. They are not linearly independent. So how do we count became quite a non-trivial question. So actually, in fact, there's only 2 linearly independent states. And these 2 linearly independent states can be obtained by the fusion rule. Remember, before we have E particle, E and E fusion give us trivial. That's a fusion rule we have before. Let me just here, they can say E and E together give us a trivial excitation. So there's E and E annihilate. But the end string here, the end string is a phi. If we put the 2 phi together, it's something somehow non-trivial. It became a trivial plus phi. So yeah, so this plus confused me many years. So I don't know what you mean by plus. We know this times means just put the 2 things together. So fusion, just grouping these 2 together means fusion. Fusion 2 extend together, we should get a 3rd extension. But here the 3rd one is ambiguous. It can be 1 or can be phi or can be their superposition of what that means. So okay, in physics it seems a little bit non-trivial. So next we'll try to explain the fusion rule. It's particularly try to explain what this plus really means. So this really led to a physical introduction of a fusion category. Fusion category actually can be defined physically. And here I try to make an attempt to introduce those fusion category using physical thinking. So we know that a gap system have this Hamiltonian sum of local operators, which give us the ground state, the lowest energy states of the Hamiltonian, or lowest eigenvalue is the ground states. Okay. So what is the excitation? Excitation really means that it's different wave function. Okay, something different from ground states, but that's a little bit too general. So here we say that the wave function for excitation actually is a ground state of a modified Hamiltonian. So we can modify this Hamiltonian by adding some perturbations. This modified Hamiltonian also have a gap. Then the new ground state of a modified Hamiltonian, by definition, is a wave function for the excitation. So that is a physical definition of so-called excitation. But however, this modified Hamiltonian has some special requirement. That is the modification is only local. We only modify this local operator in some region, like we only modify near C or near C2 or near C3. So physically, we call them traps. So the excitation is something can be trapped. So the ground states may contain excitation which are trapped by these local potentials, trap something there. So that is a local excitation. So the definition is that the local excitation is something can be trapped by these trapping Hamiltonians. Okay, and then, but however, when you're trapping Hamiltonian, the ground state may not be unique. We may have a degenerate ground state, just like a H. So actually, we have this ground state subspace. Turns out that this ground subspace became the fusion space in the category theory. So that the fusion space, a home space, is this ground state subspace. Okay. So in this language, different excitations are labeled by the trap. For different trapping Hamiltonian, we get a different excitation. But then we can modify trapping Hamiltonian continuously, and there's an infinite number of trapping Hamiltonian that's complicated. So we want to have an equivalent class. We say 2 trapping Hamiltonian is equivalent if they can deform into each other without closing this gap. Okay, so that defines so-called topological type. Okay, so this topological type became the object in the fusion category. So this the equivalent class of trapping Hamiltonian corresponds to object in the fusion category. Okay, so there's a trivial type. You know, if this class of Hamiltonian equivalent Hamiltonian contains 0 Hamiltonian, means that's a trivial type. And those trivial types can be created by local operators. So that's type 1 we discussed before. Okay, this trivial type is really trivial. It have a trivial double braiding with everything else. Okay, and there are non-trivial type which they are cannot connect to the 0 trap. They also have a non-trivial type. Okay, so here I will explain the sum. Actually, in physics, we usually don't distinguish this so-called, we only consider so-called simple excitation. We do not consider composite excitation, because in the category theory, we have a simple object and composite object. And here we have a simple excitation and a composite excitation. So what that means, the simple excitation have a property that, remember, the trapping Hamiltonian may have a degenerate ground state. If the degenerate ground state is robust against any perturbation, means if you add a perturbation, the degeneracy do not split, then that's a simple. However, in general, if you modify the trapping Hamiltonian from H delta H alpha to H beta, just modify a little bit, the degeneracy may split. If the degeneracy split, then this so that means the vector space is direct sum. So we can view this group of vector space, lower one correspond to excitation I. The top one corresponds to excitation J. So there's an accidental degeneracy. So this kind of trapping Hamiltonian trap excitation, which is I and J, degenerate, accidental degenerate. Is in physics, it's kind of like we have a trap. We trap a spin 0 particle and a spin 1/2 particle with the same energy. Spin 0, spin 1 are degenerate. So then we have a spin 0 plus a spin 1. So this is a meaning of plus, means accidental degeneracy. So that is the meaning of a composite excitation. Okay. In physics, we usually, because this is accidental, we usually don't think about that. So therefore, we only consider simple excitation in physics. But actually, it turns out that if you study fusions, you need to consider this kind of composite excitation. So from here, we can see that when we view this I and J together as a single excitation, and that excitation can be like a K. But however, it can be maybe several K, like this. When you view I and J together, they correspond to accidental degeneracy of a several K, or several K prime, and etc. And so therefore, the fusion is a special kind of trap. This special trap may have an accidental degeneracy and may have a sum. So therefore, in order for fusion to be closed, we need to include composite excitation. So therefore, the fusion rule contains sums. And so here we can say I-J fusion may have some copy of K. So number of copy is Nij(k). So this integer to say how many copy of K, or how many copy of K prime, and etc. So we can write this fusion in this. So this Nij is a fusion coefficient defined fusion rule. And here I-J(k) are simple excitation or simple object. And Nij(k) are describe a fusion between simple object. And this the ground. So fusion means physically means just bring two trap together. View these two trap as the same trap. So that's a physical way to define the fusion of tensor product. But these two traps may contain accidental degeneracy of other particles or other simple object. So we have a sum. And so basically, I try to translate from mathematical notion to physics notion. And uh, here, just want to say that the tensor product and the direct sum in the fusion category have a very physical realization. You can actually do experiments to perform the fusion procedure in the mathematics. So that's a point I try to make. And but however, the connection between physics and the mathematics is a little bit tricky because only this fusion space is a physical. That's a ground state subspace. And the I and J are a little bit more abstract concept. They are not vector space. They are type of traps, you know. And we are fusion types. So they are a little more abstract. So this is a little bit you know, non-trivial here. Okay, you can see if a C1, C2 is very close, we can view the sum of this delta H as a single delta H. You know, we can view these two delta together as a single trap, as another delta H, but live near this region. Okay. And that is viewing this sum to delta H as a third one is a fusion product. You can see the fusing to delta H is like a bring C1 close to C2. You can see. Okay. But remember, this delta H is not totally local. They have a neighborhood. If C1, C2 start to overlap a little bit, that's what I mean by they start to split. So that means if the two neighborhoods start to overlap, then you start to see their internal sum. So that means when they are very separate, they are degenerate, but they are secretly will allow perturbation which cover from 1 and 2 together, allow long-range perturbation. You see the splitting. This splitting means when you view these two as the same object, actually the sum of several different simple objects. Yeah. So this is a physical interpretation of this notion of a simple object, composite object, and the sum in the fusion category. What is their physical meaning? And the related thing that when I say the equivalence relation means that when I say deformation of delta H, I mean the deformation only local perturbation, only modify delta nearby. We should not add a perturbation which cover the whole neighborhood. If have perturbation cover the whole neighborhood of C1, C2, we're actually thinking about fusing the two together, and then we may get a different class. And this different class actually is this sum. You start to see this sum structure. Yeah. So actually this is very important because the category theory looks like abstract theory, but actually now I try to say the category theory is a very natural theory to describe physical excitations, and very natural and very necessary. And so it may not be good news for physicists. We have to learn category. We have to. There's no other choice. And but those mathematical features really can be realized in the physical system. Okay. So certainly there's consistencies. That is, when you're fusing the three objects like I, J, K together, we may get several I's, several L's. Okay. But how many L do we get? That not depend on whether we fuse IJ first or we fuse JK first. So that means these NIJK have some relations, and I won't go into details. So that's a well-known relation in the fusion category theory. So those actually define the Grothendieck ring or the fusion ring in the fusion category. But actually, that's not all. There is additional data. So there is additional data. Then this NIJK. A fusion category is more than just NIJK. Okay. So what is this additional data? This additional data is more complicated. So here I try to explain this additional data, which is called F symbol. So again, let's think about Ni fusion ijk. With fusion ijk give us a sum of several L's, and maybe other things. Let's only look at this subsector L. It has several L's. Okay. So that means the fusion space of Nijk with some other things is a sum of a fusion space of L with other things. So the dot 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 means other extension or other object. But this dot 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 is the same. So they are the same everywhere. So ijk fused with some set extension, and L fused with the same set extension. So the fusion space have this direct sum relation. So that what is the meaning of this ijk fused to several L is this fusion space, the decomposition of fusion space by direct sum. But we know that when we decompose a fusion space, a space by direct sum of some space, especially if this each part of space is kind of identical, decomposition are unique. They can be rotated by some kind of unitary transformations. It's like a choice of different choice of bases. Okay. It turns out that you're fusing part ij differently. You get a different basis. You can fuse ij first, then fuse k. Then you get a natural decomposition. If you fuse jk first, then fuse I, you get another natural decomposition. And these two natural decomposition, like the different direct sum decomposition of the same space, they differ by a unitary rotation. And this unitary rotation is so-called F symbol. So in a sense, there's some kind of morphism or isomorphism involved, because saying the two spaces are the same is a little bit tricky. Whether they are same as a space or the same together with a choice of basis. And so I think I start to learn this language in the higher category. When you say something same, it can be the identical or can be same up to isomorphism or all this kind of structure. So this F symbol is trying to say there's actually another structure is important, and we have to review it. And so it's really a different basis. Physically, you can see this way. So we can fuse. So again, we can ijk fuse into several L. So this thick bar is this space. If you fuse ij first, they split into several M's. Then we fuse M with a K, then they split further. So this M is a fusion of ij gave us M. They are splitting. Then M fused with K, we get a further splitting. Then here we get L. Okay. So therefore, that's the space decomposed into direct sum of several L's. That's the direct sum decomposition. But another fusion is that we can fuse JK first. That's fuse different decomposition. We fuse several N, another particle. JK fused to N. And N fused with I, split again. But at this stage, we get back to L. Okay. So, but now we can see that the different procedure gave us a different decomposition of a space into a sum of L's and a different choice of basis. And the choice of basis is this F symbol. So, this is physical meaning of F symbol. Okay. So we denote this F symbol in this way. So we have a ij fuse first, then fuse k, compared to jk fuse first, then fuse I. So we have ijk fuse to L. Okay, so that's this data. But however, the matrix element is that the different bases are labeled by this M and alpha beta, which I'm not going to into details. And here the different bases are labeled by N and gamma and chi. So then we have a matrix, the square matrix connecting these two bases, and we denote this way.
Thank you.
So this is the physical meaning of F symbol. But again, F symbol should be consistent. because again, that is when I fuse IJKL, different order, like if fuse IJKL, we get in one order we get one basis. We fuse IJKL in a different order. We feel KL first, J, then I. We get different bases. And these two bases are related by unitary matrix. Okay. But however, there are two ways to go from this basis to that basis. One is we use different F moves. So from here to here, we consider this part. We do the F move to move this K from here to here. That's one F move, just changing this part of graph to this part of graph. Okay, so that's one F move. Then we look at this graph, move J to the other side to go to this graph. So we have two F move to go from here to here. And we got unitary matrix connecting this basis and that basis. Okay. Or we can do three F move. We can look at this graph, move J to this side. That's one F move. Then move T to the other side. That's another F move. Then last move K to the other side. That's a third F move. So these three F move and two F move should give us same unitary matrix connecting two bases. And that's give us this famous Pentagon identity. Actually, this appear in the conformal field theory in Moss Seiberg's paper. Okay, and so actually, this Nij case and F symbol satisfy those equations. Those are data, in my mind, those are data which characterize fusion category. Certainly, there are some equivalent relation, and but in physicists we like to deal with numbers. So when people tell me fusion category is a point and arrows, and I don't know what are they. So I want to view fusion category as N and F. So that's my definition. Fusion category up to a certain equivalence relation and some constraint. And this fusion category actually is a natural theory to describe one-dimensional excitations. So it's really this picture. So we have a excitation given one-dimensional lines, they can fuse. And so the most general theory for one-dimensional excitation is a fusion category theory. So in some sense, you can say that if you have one-dimensional theory with energy gap with excitations, what is the most general effective theory? Then here we try to conjecture that the answer is the fusion unitary fusion category is the most general effective theory for one-dimensional excitations. Okay. So as an example, and we can consider this one-dimensional topological order described by Fibonacci fusion category. Okay. So in this case, we have a trivial excitation and a non-trivial excitation. And their fusion rule is just precise like this. Okay. And F symbol is following. There's a IJK O equal to IJKL O equal to phi, O equal to this excitation. And then those alpha beta O equal to O just 1. They always equal to 1. So alpha beta cannot change or have O equal to 1. But Mn can change from 1 or phi. So Mn change 1 or phi, they get 2 by 2 matrix. So that's 2 by 2 matrix. So we have this F symbol it's like this. But actually, if IJKL, one of them equal to identity, a trivial excitation, they are just identity matrix are pretty trivial. So non-trivial fusion only contain here. And here I just want to make a connection that this kind of fusion coefficient happen to be those appear here in this dancing rule of the stringnet wave function. Okay, this is not accident. So somehow this F symbol is a coefficient for us to define the dancing rule. Actually, the self-consist condition of a dancing rule is exactly the same as a Pentagon identity. remember we say the dancing rule has to be self-consistent, and the self-consistency of dancing rule happen to be the panic identity. So therefore, this really says that we can using the fusion category to construct a two-dimensional stringlet wave function, or we can use a fusion category to describe one-dimensional topological excitations. Okay, so there's a connection, and so later I will come back to this connection. So now, but here I want to say, I'll go back to my older question. What is the internal degree freedom of a phi? We know electron has spin up, spin down, so internal degree freedom is a 2. For spin 1 particle, internal degree freedom will be 3. But whether phi have internal degree freedom or not, what is that? So here we want to put an n particle on sphere. We put n phi particle on the sphere. Ask what is the degeneracy of the ground state when you have n particle on the sphere? What is degeneracy? And here I want to say that mathematically let's correspond to the fusion space of a tensor product of n phi fused to identity. And how many identity do we get? When you fuse this n phi together, you get identity. And if you get identity, that means it's okay to put this particle on the sphere. If you get this dn identity, that means degeneracy. There's a dn way to do that, so it means degeneracy is dn. So actually, the degeneracy we talk about actually is a fusion, and we ask how many ones in the fusion. And from here, we can easily show that by fusing n first, this n identity, n phi first, and then we fuse another phi, and then we can show that we can derive some recursion relation between this dn and fn. It turns out that this fn, dn plus 1 equal to fn, and fn plus 1 equal to fn and fn minus 1. So this fn actually is Fibonacci number. Okay, and so this allows us to derive dn, and when n go to infinity, and we take nth root of that, we should get a d we call the quantity dimension. This kind of represents the internal degree freedom of the excitation phi. So the quantity dimension is really internal degree freedom for this excitation phi. In this case, we find something quite amazing. The quantity dimension of the internal degree freedom is not an integer. So therefore, the topological order not only gives rise to quantum number fractionalization, it's also fractionalized degree freedom. The degree freedom is not integer. It's not fractional. It's not a rational number, but some kind of algebraic number. I was told this is actually some kind of algebraic integer. So in some sense, it is integer, but some algebraic integer in number theory. Okay.